Okay, we will now do section 11.2, which deals with chi-square two-way tests. So we're going to have two kinds of tests in this section. We have no intervals in this chapter. It's just two types of hypothesis tests. One is the chi-square test of homogeneity of populations, and the other is the chi-square test of association independence. And let's talk about when it's appropriate to do those things. So the first one, like I said, is called the chi-squared test of homogeneity of populations, or you can just call it the chi-squared test of a homogeneity. And the way to identify it is this. First of all, you have to be dealing with just categorical variables anytime you're working with chi-squared. But with the test of homogeneity, you're going to have two populations, and you're going to compare those two populations in regards to a categorical variable. And of course, since you got two populations, you're going to have two independent samples. So we're going to have two samples, and then we're going to have one categorical variable that we're going to compare between the two. One categorical variable. So it could be we want to know, is there a difference in the political party affiliation? Let's say that's our variable between the people of Mississippi and between the people of Alabama. So that's two different populations where we would take two different samples. We want to know if there's a difference in religious affiliation between, let's say, the males and females of this state. So that would be two populations, the males and the females. Now the other kind is a very similar kind, and actually the mechanics are going to be almost identical in this other kind. It would be, and I'll just write it like this, chi-squared. That is the Greek letter chi. That's not an X. So it's a chi-squared test of association or independence. Association or independence. Association or independence. And it will look very similar, except the main difference is the terminology and the sampling method, because here you're just going to have one population. You're going to have one population, and thus you're just going to have one sample, but you're going to be comparing two variables, two categorical variables. And so the wording will be, it'll say, is there a relationship? Is there, let's say, a relationship between, let's say, political party affiliation and race amongst a group of people? So is there a relationship would be kind of the giveaway term there. Or is there an association? Or is there a correlation between, political party affiliation and, let's say, what state people were born in? And so the key thing to notice the difference, I think, is the sampling method. And that being, this one is two samples and this one is just one sample, but it's comparing two variables. And so the key words to look for when you're looking at these problems, first of all, once again, please, it has to be categorical variables, but you're looking for the word association would certainly be a giveaway, or the word independence, or relationship or correlation between the two variables. And then the key word you're looking for in the stem of the problem here is the word difference. It'll frequently say, is there a difference in these two groups in regards to whatever variable it is? Is there a difference in the people at this school and the people at this school in regards to, let's say their race or some other categorical variable? Or is there a difference in the trees in this forest and the trees in this forest in regards to the type of tree? So that's your little introduction. So our first example is going to be how you do a chi-squared test of homogeneity, and the second one is going to be how you do a test of association independence. And like I said, the mechanics are going to be basically sort of the same thing here. It's just your terminology is going to there's going to be a difference there. So let's look at this problem. So it says a researcher wishes to see if there's a difference. There's a key word. There's a difference in the male and female adults in the city in regards to political party affiliation. So that is, a categorical variable. And we're dealing with two different populations here, the male and females for this city. She takes an SRS, that's certainly a big deal to us. It means we have a good unbiased sample there of 60 males in the city, and finds 40 are Republican, 10 are Democrats, and 10 are other political affiliations. She takes another SRS of 40 females and finds that 10 of them are Republican, 20 are Democrat, and 10 are other. First of all, draw an appropriate graph to compare the males and females, and then perform an appropriate test. Now, the appropriate graph is going to be a side-by-side bar graph, and that's what we did in Chapter 1. So this is the kind of problem where you can hopefully see where the whole year is fitting together. So drawing a bar graph just like we did in chapter 1, and just analyzing how the data was collected like we did in chapter 4, and of course doing statistical inference here. But just drawing out our bar graph here. So we've got males and we've got females. And of course, anytime you're drawing a side-by-side bar graph, we need to come up with our conditional distribution, and conditional being, in essence, the percents of each, Democrat and other. And so this would be our two-way table that we're drawing. You certainly could be asked to do that. So in regards to the males, we've got 40 Republicans, we've got 10 Democrats, and we've got 10 other. And then in regards to the females, we've got 10 that are Republican, 20 that are Democrat, and 10 that are other. So let's come up with our marginal distribution. So with our marginal distribution, we've got a total of 60 males, and we've got a total of 40 females. And then for the marginal row distributions, we've got a total of 50 Republicans, we've got 30 Democrats, and we've got 20 other. And so we add these up, and we've got a total of 100 people that are in these two samples that are in our study. So in order to make the graph, I need percents. Now you could do this by row or by column. So what I'm going to do is I'll do it by column. I want to know the percent of males that are Republican. So I'll say 40 divided by 60, and so that's 0.6 repeating. So I'll just put that right there. 0.6 repeating, and then what percent of the males are Democrats? 10 divided by 60, that would be 0.16 repeating, and same thing with the other, 0.16 repeating, or a little less than 17%. For the females, 10 out of 40, or only 25% are Republican, and then 20 out of 40, half of them are Democrat, and then 25%, so this would be 0.25 are other. And so that would be our conditional by our columns. Now, if you did it by row, you could do it by that as well if you wanted to. You could say, well, what percent of the Republicans are male? And so that would be 40 out of 50 be 0.8. And then a female be 10 out of 50 be 0.2, and so forth. The percent that are Democrats, and go, well, the percent of Democrats that are male is 10 out of 30, or 1/3, 0.3 repeating, and so forth. But we'll do it like this. And so we'll make our little side-by-side bar graph, make sure to properly label things. And so this is, in essence, we'll go with our percent of people here. Now, our highest percent is going to be that 0.6 repeating. So I'll just go up to 70%. So I'll go 10, 20, 30, 40, 50, 60, 70%. And so, of course, this is 10 and 30 and 50, let's say. And so then we will say, okay, well, let's go with, we'll go with Republican, we'll go with Democrat, and then we will go with other. So we will go with other. And so in regards to the males, we have 60% Republican, or 66.6 repeating, so that'll go up to about right there. And then in regards to females, it's 25%. So you can certainly see the big difference there. And so my little key here, so for my little key, so this will be males, and my filled in one will be females, like that. And so for the Democrat, we'd have 0.16 repeating for the males. So that's just doing this as neat as I can. And then all the way up to 50% for the females. And then lastly for the others, so that goes up to about 17%, and this goes up to 25%, which is something like that. So if we were asked to comment on that, of course, if it was quantitative data and we commenting on that, we would say, we would cuss. But with categorical data like there, we just describe what we would see, and we would say, well, when you look at this, the males are much more likely to be Republican, and the females are much more likely to be Democrat or other. And so that's all you would have to say. And so that is what we did in chapter 1. But now we're asked to draw a test, or we're asked to do a test. And this is categorical data, and categorical data means we are going to do a chi-squared test. And of course, we're going to do our THAME acronym whenever we do a test, and I'm going to show you how we calculate everything. So the first thing is the type of inference. We notice there is 2 different samples taken in regards to the chi-square. With 2 samples, it's homogeneity of populations. We're basically asking, are these populations homogeneous? In other words, are they the same? Okay, which just looking at this graph, they don't look to be the same. I mean, the males look to be much more likely to be Republican in this group, and the females look much more likely to be Democratic. But is it statistically significant difference, or is it plausible that difference is due to sampling variability? That's sort of the question we're going after. So the type of inference that we're dealing with here, and this will be a chi-squared test of homogeneity of populations, and you can just call that the chi-squared test of homogeneity. Just like that. There we go. And so you have to memorize the names in this chapter. And they're a little bit complicated, but it's important that you do that. And of course, the next thing we do is write our hypotheses. So now, our null hypothesis is that there is no difference in the two populations. So that is, and with the test of homogeneity, that's always your null hypothesis. There is no difference. There is no difference between the males and females. Obviously say this in context. The males and females of this city in regards to political party affiliation, and that the alternative is that there is a difference. There is a difference. And you can certainly use ditto marks here in regards to the males and females in this city in regards to political party affiliation. So there's our null, and there is our alternative. We then go on to our, so we must verify our assumptions. So we must verify our assumptions. Okay, now this is going back to the fact that we've got two samples. It's no longer sin, it is I sin. And the other difference in this chapter, don't ever say the word normal in this chapter. We don't have normality. It's that our large counts conditions is going to be that all the expected counts have to be at least 5. And I'll show you how to calculate those in a minute. So we had to have independent random samples, or of course, if it was an experiment, we had to have random assignment to treatments. But in this particular one, it clearly says SRSs. So if it says SRS or random, then you're good there. And if it's clear that they aren't influencing each other in any way, then they're independent. So you would just say this: it says SRSs were taken, thus independent random condition is met. Anytime you have two samples, they have to be done independently. So, and you must say it just like that. So, and then we have our other aspect of the word independence is because we're not using replacement, we're doing sampling without replacement, our population size has to be at least 10 times our sample size so that we aren't significantly changing our population by taking people out of it in this case. And so you would say, well, we have two populations here, the males and the females. So you would say there must be at least 600 males, that would be 10 times the sample size of males, and 400 females in this city for our population sizes, there's two of them, to be greater than or equal to 10 times our sample sizes. And you can write them like that. That's standard notation for population size and sample size. So there you go. And then lastly, not normality, is our expected counts. All of our expected counts have to be greater than or equal to 5. And I'm going to show those, and you have to write them down. Okay, now I'm going to show them in a minute, so I'm just going to write shown below here. Okay, but you have to write them down. I'm going to show you how to calculate them. Anyway, and don't say the expected counts are greater than or equal to 5, thus normality is met. Don't say the word normality. So what this ensures that my test statistic will follow a chi-squared distribution in repeated sampling, which that is going to be explained in another video in regards to this chapter. But let's talk about how you do expected counts. This is a little bit complicated, but but it's really not that bad. And so in order to find our expected counts, so this is what we got to do. Let me rewrite our matrix here, our 2A table. So we've got males and females, and we've got Republicans, and we've got Democrats, and we've got others. And of course, we've got 40 male Republicans, and we've got 10 Democrats, 10 other, and then we've got 10, we've got 20, and we got 10, and then we need our row and table total. So this would be, we've got 60 males, and we've got 40 females for a total of 100. That's our table total. Then we have our row totals, which is 50 and 30 and 20. And so there we go. Now, here's the rule for our expected counts. So in regards, and this is going to be true for the next test as well. This is true for this whole section, for the test of homogeneity and for the test of independence. Your expected counts for each cell is going to be the row total times the column total over the table total. Now, and hopefully this will make intuitive sense here. Now, so what we've got here, if you think about it, now the null hypothesis is that there's no difference in the males and females in regards to their political party affiliation. It's certainly different in the sample, but the null hypothesis is in the population, there's no difference. Well, in our total group of people here, 50 out of 100 are Republican. If you look at our row here, 50 out of 100 are Republican. So if there's no difference in the males and females, we're expecting 50 out of 100. In other words, 50% of each to be Republican, if in fact the null is true. So if the null is true, and that's the whole reasoning we do in hypothesis testing, we're saying if the null is true, all right, what's the probability we'll get sample values this unusual? Well, if the null is true, in this sample, we're expecting 50 out of 100 of each of them to be Republican. Well, we've got 60 males here, a total of 60 males. So if 50% of them are Republican, the expected value here is going to be 30. We're expecting 30 of the males to be Republican if the null is true. And then with the females, we've got 40 females. Well, if the null is true, that means 50% of them would be Republican. And so we've got 20. That is the expected number of females. And then with Democrats, in the combination, the total group of people here, we got 30 out of 100. 30% are Democrats. So if there's no difference in the males and females, we're expecting both of them to have 30% Democrats. And so, well, 30% of 60, so that's going to be 18. So that is the expected number of male Democrats. And then with the females, we're expecting 30% as well. And so that's going to be 12. That's just going to be, 30% of 40. Or in other words, if you do this table, if you do this formula here, row total times column total over table total, well, when you look at this, it's just going to be the row total's 30, the column total's 40, and the table total's 40. So it'd be 30 times 40 over 100, which is that. And then similarly with the others, we're expecting 20% of each of those. And so 20% of that, well, that's going to be 12. And then 20% of 40, that's going to be 8. So those are our expected values. Anyway, and you could use that reasoning. You could go the other way as well. You could say, well, we're expecting, you got a total of 60% of these people are male. So therefore, we're expecting the Republicans to be 60% male. So it'd be 0.6 times 50, which would be that, and so forth. And we're expecting 40% to be female. So that's how you get your expected counts, and that is something that will be asked of you. Now, then to find our chi-squared test statistic. Now, let me just go ahead and say this. Yes, there's a shortcut with your calculator in regards to all this, but you have to understand what I just said. You have to be able to use this formula, and you have to be able to calculate the chi-squared test statistic by hand. So, all right. And by the way, so like I said, in regards to your conditions where you said shown below, you have to write down what your expected counts are. And so in this case, these are our expected counts. So these in parentheses are expected counts. And so you have to clearly show that you know what the expected counts are. And they're all bigger than 5, so therefore the distribution we're working with will be a chi-squared distribution. Now we've got to do our mechanics, which is, to do our mechanics, we've got to come up with our test statistic, our p-value, and our degrees of freedom. There's the formula for our chi-squared test statistic. It's the observed value minus the expected over the expected. So let's calculate this thing out. So what we'll have to do for each of these 6 cells, our chi-squared test statistic is equal to the sum of the observed minus the expected squared over the expected. So if we're doing this by hand, we would start here. Well, so that's going to equal to 40, the observed, minus the expected, 40 minus 30 squared over 30, like that. And so that, as it turns out, is equal to 3.3 repeating. That is what is known as the component of chi-squared that comes from this cell, which will certainly be asked to be. Then we'll have to plus, do it for the next cell. That's 10, the observed, minus the expected, squared over the expected, which is 20. And so that would end up being 5. If you were to calculate that out. So that is the component for the female Republicans, plus, and we kept going on, so we'll go to the male Democrats, and so we just say the observed minus the expected, squared over the expected, and so that, as it turns out, is 3.5 repeating. So that is the component there, and we kept going on. So this would be for the female Democrats, so that'd be 20 minus 12 squared over the expected 12. That, as it turns out, is 5.3 repeating, and then plus, and then this would be 10 minus 12 squared over 12, and that just ends up being 0.3 repeating. And then lastly, the 10 minus 8 squared over 8, and so that would be plus 1/2 plus 0.5. And if you were to add up all those numbers that I just circled, that gives you your chi-squared test statistic, which in this case would be equal to 18.05 repeating. So that is our chi-squared test statistic. And those are the components. Like that, these are the components of chi-squared. You'll be asked about that. What's the component? Let's say for female Democrat. Well, female Democrat, so that's going to be this one right here. So it's contributing 5.3 repeating, which is more than any of the others, which means in essence, it has the biggest relative difference. It's the one that is off the most, so to speak. It's the one where it's observed relatively minus its expected is kind of the biggest number. So there we go. Now, the next thing you need to know is your degrees of freedom. Now, the formula for the degrees of freedom for the 2A table, chi-squared, is number of rows minus 1 times number of columns minus 1. So in this case, our rows, there's going to be 3 rows. So this is going to be 3 minus 1. The number of columns, and columns go up and down like columns in a building. Okay, so there's just 2 columns, so that would be 2 minus 1. And so that's going to be 2 times 1, 2. That is your degrees of freedom. You have to write it down. That tells us which chi-squared distribution we're working with. So it tells us which chi-squared distribution we're working with. So anyway, and now to find your p-value using the table, we would use this and we'd say, okay, let's go to table C, and we are going to degrees of freedom 2. And so this whole row deals with, there's my chi-squared test statistic, and then the top row tells us our p-value. And so, and in this case, our chi-squared test statistic, a little more than 18. So we would go to a little more than 18, and guess what? It's off the table. Okay, so we know the p-value. So this area, so in this graph shows, in essence, the probability of getting this chi-squared value or more unusual. So it's going to be less than 0.005. It's going to be, really close to 0, actually. So our p-value from the table, p-value is less than 0.0005. And so that would certainly be a statistically significant result, and we would say this p-value is below 0.05 or whatever the alpha is, and so we would reject the null and favor the alternative, which we would say in context. Now, once again, let me remind you how to use chi-squared CDF to find this. So what you can do once you find your Once you find your chi-squared test statistic and your degrees of freedom, you can say, well, I'll use chi-squared CDF. So we'll go second distribution, and we'll go down to chi-squared CDF right there. We'll never use chi-squared PDF. And so, and a chi-squared is always going to be that value or bigger. Because it's squared, it's always positive. And a p-value is the probability of getting that or more unusual. So it'll always be your chi-squared test statistic to infinity. Our degrees of freedom is 2. And so we hit paste. And there's our p-value, which is really close to 0, about 1.2 times 10 to the negative 4. So our p-value is equal to like 1.20 times 10 to the negative 4. And so it's really small. And so our conclusion, so last thing, our ending, so we would say this. We would say this p-value, which is approximately 0 really, is less than our alpha. Now, we aren't given an alpha, so it's really sort of supposed to be decided on before the problem, but if you're not given one, just use 0.05. It's less than 0.05. Thus, I reject the null hypothesis. P-value is low, you reject the null. Okay, thus I reject the null hypothesis. Thus, I have convincing evidence for the alternative, which I'm going to say in context. Thus, I have convincing evidence that, and then you bring back where our alternative is. So the alternative is that there is a difference in the males and females in this city in regards to our political party. So you just restate, I have the alternative. I have convincing evidence that there is a difference. There is a difference between the males and females in this city, all of them in the city, the whole population's here in the city in regards to political party affiliation, in regards to politics, let's say. And so there we go. Okay. That is how to do this by hand. And I realize this is pretty tedious and everything. And yes, you need to understand that and so forth. But guess what? We have, with your mechanics, the only 3 numbers that you officially have to write down are your test statistic, your degrees of freedom, and your p-value. And so let me show you how to quickly do that. So what we're going to do with our calculator, and this is going to be the same thing with the next test as well. This is going to be, in essence, the same thing when we do a chi-square test of association and independence. We're going to put our observed counts in a matrix. Now, the matrix menu is right there above the x to the negative 1. So we're going to use the matrix menu. And so here we go. So I go second matrix. And then what you're going to do is you're going to arrow over to edit matrix and edit matrix A. And I always put the observed in matrix A just so that I don't get them mixed up. So the observed is going to go in matrix A. Now this matrix right here, so this is a 3 rows and 2 columns. So it's 3 by 2. So it's 3, enter, 2, enter. Now if you mess it up, the wrong shape won't appear here, and so you just go back and change it. So let me enter these numbers. So it'll be 40 and 10 and 10 and 20 and 10 and 10. Can't believe I did those right. Now, it's going to automatically calculate the expected values for you, which is really convenient. So anyway, so that's all you have to enter in. It'll automatically do the expected counts. Like in a chi-squared goodness of fit test, which we did in section 1, you have to, you've got to calculate the expected counts and put those in list 2. But you don't have to do that here. This is all you have to put in. And now we do stat, tests. So stat, tests, and we go down to chi-squared test. So we scroll past all this stuff we've done in the past. We use, that's the section 2, a chi-squared goodness of fit. That's section 11.1. This is section 11.2. Both of the tests in section 2 is this test. So observed is in A. Now, by the way, if it didn't say A there, let's say there was nothing there, you would just, you would go and it's highlighted. And so you go back to matrix. So you go second matrix and then just hit enter on A. And it'll put A right there. And so, and then it's going to store the expected counts in B, which I'm going to go access, and then it'll do calculate, and it tells me my test statistic, my p-value, and my degrees of freedom. So that's certainly a lot easier So there you go. But now it's important that you always write down your expected counts. So in order to see the expected counts, you can go look at matrix B. So if you go second matrix, and the easiest way to look at them is just to go edit matrix B, I think. So we're going to go edit matrix B just to look at them. And so there's our expected counts. And by the way, most of the time expected counts are going to be decimals. Okay, so don't round them to the nearest integer. That's an important thing, actually. You can round them like to the 100th place or whatever, something like that. But just write them down however they appear there. So that's how you do your expected counts. And so there we go. And so you could quickly do those. You could quickly use those to calculate your components. And like I said, you will be asked about the components. So all right, so there you go. Now let's do the chi-squared test. Association independence, which is a very similar sort of thing. It's just your sampling techniques is going to be different, and your terminology is going to be different. So okay. So all right, here we go. So the key thing to notice in a test of association independence, it looks really similar. You're going to have these two-way tables here. Almost all the time, they'll just give it to you in two-way table form like this. But the key thing is is it one sample or is it two? And in this case, you notice that it's just a random sample and you got two categorical variables, and that's a chi-squared test of association independence. It's basically asking the question, are these two variables associated? So let's look at this one. It says an educational administrator wishes to see if there's a relationship. That's kind of a giveaway word for association independence. If it said there's a difference between, that would be a test of homogeneity. Is there a relationship between how advanced the student is and his or her opinion about whether or not the school should have stricter discipline policies, which they have defined in a categorical way. It's categorizing them in both ways. So he takes a random sample of 89, so that's certainly meeting a condition of randomness, of the students and gets the results below. Perform an appropriate test. And so I'm not going to write all this out entirely, but because a lot of it's really similar to what we just did. And so the type is, this is a chi-squared test. Don't call that x squared. Chi-squared test of independence, or you could call it a chi-squared test of association. So there we go. All right, our hypotheses. Our null hypothesis is always going to be that there's no relationship between the two variables. There is no relationship, or you could say there's no association, or there's no correlation. There's no relationship between the level of the student. So the level of the student and opinion on discipline, we'll say opinion on discipline, for the students of this school. Now that's our population here. For the students of this school. That is where we got our random sample. So those are the ones we can generalize about. And we can't safely generalize about others unless we have reason to believe that they're like them. But anyway, and the alternative is that there is a relationship. There is a relationship. There is a relationship between these two things. And so that is always, when the chi-square test of independence is always going to be there, the null is always that there's no relationship. The alternative that there is a relationship, and we can put ditto marks as opposed to writing all of that stuff again. Now, the other way of wording this would be to say that the null would be is that these two variables are independent. That's what no relationship means. It means they're independent. So you could say the null hypothesis is that the level of student and the opinion and discipline for the students of the school, they are independent. And the alternative is that they are not independent. Okay? Our assumptions are really saying we only have one sample here, so it's not I sin. But isn't it, it says random sample, and so you would write all that out. Our population size must be at least 10 times our sample size, because once again, we are sampling without replacement here. So you'd say there has to be, at least, there has to be at least 890 students at this school. And then no normality. Don't say normality in this chapter. All the expected counts. All the expected counts. are going to have to be greater than or equal to 5, and you must show them. You must show them, and don't say normality. Just say it like that. So we got that. All right, and so what we'll do to do our mechanics, now we could, of course, I'm not going to go through how to do this by hand like on the other one, but you would, once again, to get your expected counts, you would get your marginal distributions. You would say there's 28 and there's 48 of the average level, and the advanced level, that's 23, and that should add up to 89. Let's see, did I add those right? So that's 28. So these add up here. So these add up to 53. And then these add up to, so these add up to 46, and it's actually 99. So yeah, that was a mistake. So this should, I'm sorry, this should say 99. There's a total of 99 there. So that was a little error in my question writing. But as I said, so to find the expected counts by hand, so for this cell, for low level yes, let's say, that's going to be the row total, 28, times the column total, 53, over the table total, 99. And you would do that, and so that would be the expected count for there. And you do that for all of them and so forth, just like I just explained. And then you can find your chi-square test statistic. But I'm going to go ahead and do this with the calculator. So with the calculator, what we'll do is I'm going to enter this into a matrix. And once again, the matrix, so I go second matrix, and I go edit. And so this is once again a 3 by 2, so I hit enter. This is a 3 by 2, 3 by 2. And so then I enter those numbers 12 and 16 and 27 and 21 and 14 and 9. Okay. And so 12. So there we go. Okay. And so now I'll do my chi-square test. So I do. And once again, it's going to calculate the expected counts for me, which you're expected to write them down. So I go stat, test, and I go scroll all the way down to chi-square test. So I go to chi-square test like that, A and B. So it's going to store the expected in B, and I go calculate. And so there is my test statistic, my p-value, my degrees of freedom. So in the mechanics part of this test, you have to write down those three values. So our chi-squared is equal to 1.923. Our p-value is equal to 0.38. And our degrees of freedom is equal to 2. And so what you would say there is this p-value is above 0.05, so we fail to reject the null. We do not have convincing evidence. That, and then restate the alternative. There is a relationship between, the level of the student and their opinion on discipline. And then, of course, we have to write down our expected counts. So to look at those, we would go second matrix and just edit matrix B. And so there's our expected counts that you would certainly have to write down. Then the last thing that I failed to mention would be to do what is known as a follow-up analysis. A follow-up analysis is when, and let me just go back to the previous problem here. A follow-up analysis is when you go back and you look at each of the cells and you ask yourself which of the cells is contributing most to the chi-squared. And so our follow-up analysis in regards to this one, we would look and we would say, well, here's the components of chi-squared, these numbers that I've circled there, 3.3 repeating, 5, those 6 numbers. And so we would look at that and we would say this cell, well, that cell I believe that would be the female Democrat. And so what you would do in your follow-up analysis, you would say, well, the female Democrats contributed the most at 5.3 repeating. And then the next one is this cell, which that one is the female Republican. And then you'd say the female Republican also contributed a lot. So they contributed 10.3 repeating to the 18. So more than half of your chi-squared is coming from those two cells. And so that's what follow-up analysis is, going back and looking at your components of chi-squared and saying which ones, in essence, contributed the most. Okay, so that's it. Thank you for paying attention, and I wish you all the best in regards to chi-squared two-way tests.